Well, thank you for the introduction. And so I'm Anton François, and I will present you our implementation of the metamorphic registration algorithm. So I just have to figure out how to pass slides.
Sometimes it's tricky. Yeah.
And okay, great. So yeah, when doing image analysis, we often need to register images which have the same structures in order to do normalization or segmentation, as we just saw in the previous talk. And for this, we have a set of algorithms, which are diffeomorphic registration algorithms. For example, Dartel and Demon, or in the most used maybe now, which is LDDMM, introduced first by Trouvé. And the thing of this algorithm is that have these diffeomorphic properties, which are not always very useful. Actually, in our case, in my PhD thesis, I want to make some glioblastomas atlases. Glioblastomas, we just saw, are like brain cancers. And so if I will need to do some registration of a healthy brain, which are with a healthy template, to a cancerous brain. And so here the major flaw is that we have not the same topology of the two images. Like there is one here, like there is one big cancer at the center that will change the topology, change the appearance of the surrounding area and the shape. So hopefully we have an algorithm there, which is called metamorphosis, that can break this diffeomorphic assumption, keeping the diffeomorphic deformation, which had one flaw, which was not implemented. Actually, there was no implementation available. So it's what we did here. So just to give you a quick example of why bother and how does it work. So if we want to register the source image here on the target, which is the next one, and this picture here is just the superposition of the two images. So the two images are in one channel. So the yellow part are the well-matched part. So this is just the source and registration. So if we do the LDDMM, which is like diffeomorphic algorithm, we won't be able to lose the topology of the source image. But metamorphosis will conduct to a almost perfect match. But we see that if we just take the deformation here, we will have almost perfect match here. Like a good diffeomorphic matching. Okay, so how does work metamorphosis? So it's really based on the LDDMM frameworks, but at each time step of the image evolution, we will add some intensity change. So if we have to write it in the variational form, I hope that you all see. So we take the time derivative of the image I, and it's just the deformation, like the action of the vector field, plus some z here, which we'll call the residuals. Why the residuals? It is because if we just rewrite the equation and isolate z, we can see it as the difference of the temporal derivative of I minus the vector field action. So yeah, we set all our vector fields, which are smooth enough in a vector field, and we also give the norm, associated norm, which will be like RKHS norm with a Gaussian kernel of parameter sigma. Yeah. So just wanted to show it. So actually, what is metamorphosis? We can also see it as an optimization problem when we have to look at the minimal path, so the geodesics, in between 2 points in the image space or in the natural image space. So E0 is the first image, so we set it as the source image. E1 here is the target image. And so we will find the smallest path with this norm, with this metric here. So we define a metric, and with this metric, we can find a set of equations which give us here the geodesics. So just by following this. So those who are a bit familiar with some fluid mechanics will recognize here the continuity equation here, which also is the momentum. And here the advection equation, which is really the deformation part. So actually, by following this geodesic, we have an interesting property, is that we have all norms, all the norms, the V norm and the L2 norm of that are constant over time. So that will be needed for the next thing. So we can also, from the geodesic here, express V0 from the initial vector field from the initial residual and the source image, the derivative of the source image. And with these both results, we can now simplify our cost. So we can lose the integration over time, and we can also re-express the initial the geodesics only from Z0, the initial residual. So this will allow us to make some geodesic shooting. So we compute E1 from the geodesics, and so here is the integration over time, and we computed all the vector fields and the residuals with the previous equations. And what we will be doing, what we will do for the geodesic shooting is that here we just set an initial Z0, we compute E1, and then we will decrease the distance in between E1 to the target image by optimizing this functional. So here we have the data term, which is just a very simple L2 norm, and we have a regulation term that is controlled by lambda, which is a parameter, and which is our So if we set lambda to 0, we have an exact matching problem, but we choose to keep the regularization. So I just want to quickly show you how does it look like a geodesics. So this is nice. This is a geodesic. So this is the initial Z0, and if we make the evolution over time, it does look like that. So this is just a nice feature. Okay, but now comes the main point of the talk. So actually, doing the integration is less easy that it seems to. So we have to improve a bit the integration scheme. And so when we are working with flow and integration of vector fields, we often talk about Lagrangian and Eulerian formulation. Lagrangian one is the one when you follow stream of points, which are really not suitable for images, and the Eulerian formulation, where we have an images and we look at one pixel, for example, and we look at the variation of this image by a flow that's going through it. The only thing is that it's very, very sensitive to the time step using, and if we take a too small time step, we will have like bad results, like divergence and everything. So we can use a semi-Lagrangian formulation, which is kind of the compromise. So we deform a grid, and then we have to reinterpolate the deformed grid on this. So I guess the time is not right, because I don't have 17 minutes left.
Oh yeah, no, but you can go.
Okay. So just if you took back the equation here, here is the advection thing, and we write the characteristic equations, which are these ones. So we follow the fields. What we can do to do this is just interpolate the image here. We interpolate here this part we interpolate on the reverse, the different grid, and then we add the residuals here. So the same thing is applied here for the residuals, with the only trick that we have to split the divergence in to get back advective term here, and here just the divergence of V multiplied by 2V. So this is one optimization step of the integration. So in either Eulerian formulation here and the semi-Lagrangian formulation here. So the first step here is to compute the grid identity minus the vector field that we computed, and then reinterpolate the quantity we just saw before. So this was implemented in our library, which is called Demeter. It is implemented with PyTorch for the use of auto-differentiation, which is a lot the code. And so it is GPU compatible, and it's actually quite fast to perform this on big images. And so it is available here on the Query code if you want to check it. So we'll look at some stability results. So if we look at the Eulerian integration here, so with 15 integration steps, which is a lot for this kind of method, we see that we have very, very bad results. This is the same geodesic that we saw earlier in the presentation. And so we see like very bad divergence term here. And actually the next step, if I would like have 49 integration steps, we would just have like some divergence and everything. If we just use the semi-Lagrangian integration only for the advective term or only on the image, so we see that it's better. We have an evolution that looks like something that we want, but we have a lot of instabilities in the residuals part, which is still something that we don't want. So with the trick that I just explained, we have here the good integration, which is quite rather stable and quite fast. So, and I just want to show you some results on some play example that I made for the occasion. Sorry. So here's the source image. Here's the target, which is the same image, but we added some cancer, because why not? And we deformed the surrounding area. So here you have again the comparison. The yellow part are the one which are equal, and here there was some deformation happening. And so if we just follow the integration, it's jumping a bit, but yeah. So we saw that LDDMM did actually a rather good deformation, but with the metamorphosis, we can also describe the growth of the cancer, and we can also, and we hope actually in the next walk to recover which place induced topology change. So, okay, quickly, I want to introduce you to some the parameters of our method, which are lambda and rho, the parameter of the regularization term, the sigma here in the geodesics, which is defined in the V norm, and the mu here, which is the amount of deformation we add to the model. So actually, the choice of mu is quite important in the thing. If we choose mu too small, we'll just have LDDMM evolution. If mu is too big, we have the registration that will be made only by intensity changes, which is not very interesting. And so the challenge here is to find the good mu, which gives you the right amount of deformation of intensity changes. And obviously, by choosing this parameter sigma, you can also have more regular fields, vector fields at the end. Yeah. So in conclusion, yeah, we provided both a joint framework to do LDDMM and metamorphosis in the method that we presented on Demeter, with some robust integration scheme implemented in Python and some encouraging results that we are eager to improve soon in the next works that are coming. So thank you for your attention, and if you have any question.
Any question? Yeah. Can you come near the Zoom, because people will not understand you, but okay, you can put off the mask.
So a simple question: if you need to be in 2D, you are in 3D.
Yeah.
Your method is still working?
Yeah, it's still working. Actually, now there is still some issues with it, but very soon it will work. So actually, in the next months, it will be fixed and it will work in 3D. It's the aim of the method.
Because in this domain, it was much more difficult in 3D.
Actually, so I didn't really try it yet, so maybe it is, but I didn't. Okay.
But so your trick is to use something between Eulerian and Lagrangian.
Yeah.
Dynamics. Yeah.
Yeah. But this is done by interpolating, and the key function here is the interpolation, and the interpolation in 3D is now working quite well also. Okay. So I guess it won't have any problem.
It's a good news.
Yeah. Thank you. Yeah.
So you mentioned that this Eulerian integration scheme is quite sensitive to the choice of the time step.
Yep.
Can you explain why that is?
It's actually the CFL condition, which is the Courant-Lévy-Fréchet condition, which actually is just like quite known in the integration theory, that if you just take two big steps, you have the approximation of the Eulerian thing is too big, and then you go out of the integration scheme and you go out of the manifold, and it's a very like a bad thing of the Eulerian integration.
Okay. Yeah. So is does it work not so well when it's too big and also when it's too small? Or
actually, it's better when it's very small. But the problem here, why we can use two small integration steps. Okay, first the time, but maybe that's not most important. But most importantly, if we use very small integration step, then we'll have a very complex time vector fields also. Because we'll have like, maybe if we use like 15 integration steps, then we have to integrate over 15 vector fields to then compute the deformation, which actually what I saw leads to kind of weird results.
Okay, so, thank you.
Okay.
Someone, another question? I have a question. Okay. How do you deal when there is a global transformation of intensity, as in the first picture?
Transformation.
Because sometimes there are some variation with MRI device, for example, some global variation of intensity. Is it possible? I think it's possible to take it into account in your global minimization framework, or because you show one image where this is the case, the first example, I think,
like
at the very beginning.
Here, yeah, I guess, yeah. So this one? No, this one. Yeah. Okay.
We can see that there is, and this is the case in MRI. The intensity must be standardized in order to compare different results. So, is it possible to take it into account directly in the criterion or even to estimate this transformation of intensity, both with the deformation?
So actually, so there is many way to answer I guess. But so first, maybe as you, I guess, we will work with normalized, normalized images if we really need to do the registration. Then if we really need to register a picture that have like the global intensity, which are not the same, then actually the L2 norm here, actually the data term, it will be the most important to choose. And with the L2 norm, they will choose to match the closest intensity thing. So if it's too far away, obviously we won't achieve a good registration, but if it's close enough, I guess it will work. And then with the metamorphic thing, we will also fill the gaps kind of the difference of intensities. But I don't know how it will evolve. But I guess for the real application, we will use anyway like pre-normalized images for this.
Okay. Thank you.
Thank you. You're welcome.